Hi, my name is Mark Rulo. I'm one of the mathematics consultants in the Learning Success Center at Mount Wachusett Community College. In this video, I will explain hypothesis testing for proportion, variance, and standard deviation for your statistics class. If you haven't already done so, please check out the video for hypothesis testing for the mean. It will give you some background to hypothesis testing and to what we'll be doing in this video. Quickly, when we make a claim, it is a claim about a population parameter. It may be difficult or impossible to count every individual in a population, so we'll take a sample instead, and we'll make a conclusion about the population claim based on that sample. Sometimes we want to make a claim about the percentage or proportion of a population that has some quality or response. For example, we will make a claim about the proportion of the population, P, who thinks dark chocolate is the best kind of chocolate. Like in previous examples of hypothesis testing, we need to make sure our distribution can be approximated by a normal distribution. For proportions testing, we do this by first verifying that n times p and n times q are both at least 5. Remember, n is your sample size, and if P is the proportion or probability of a yes or a success, then Q is the proportion or probability of a no or a miss, and Q equals 1 minus P. We can choose one of two methods to conduct the hypothesis test for proportion. As we did for hypothesis testing for the mean, we follow a certain algorithm for hypothesis testing for proportions for whichever method we've chosen. In method 1, we compare a critical value or critical values to a test statistic. Step 1. Verify n times p and n times q are at least equal to 5. Step 2. Write the claim down mathematically and assign it as either h0 or h alpha, depending on whether or not it contains a condition of equality, and then write down its complement. Step 3. Identify the level of significance, alpha, and from the z-table, determine the critical value for a one-tailed test, or values for a two-tailed test, and identify the rejection area or areas. Next, we take a sample of size n of that population and find what proportion of that sample has the quality or response we are looking for. The sample proportion is called p hat. Use p hat to calculate the value of your test statistic, z, by the formula z equals p hat minus p over the square root of p times q over n. Finally, compare the value of the test statistic with a critical value or critical values and determine whether or not to reject h0, and interpret how that affects the original claim. For example, let's test the claim that the proportion of the population who prefers dark chocolate is greater than 60%. Use a level of significance of 1%. First, we verify that NP and NQ are both greater than 5. They are, so we proceed to stating our claim mathematically. P is greater than 0.60. This claim does not contain a condition of equality, so it is H alpha. Our complement, the null hypothesis, becomes the proportion is less than or equal to 0.60. Our alpha is 1%, and this is a right-tailed test, which we know because of the direction of the inequality in H alpha. Using the z-table, I see the critical z-score is 2.33. And let's draw in our rejection region. We take a random sample of 100 people, and 65 said that dark chocolate was their favorite. So p hat is 65 divided by 100, or 0.65. Now calculate the test statistic. The test statistic z equals p hat minus p over the square root of p times q over n. And I get 1.02. Our test statistic does not fall in the rejection area. Therefore, we cannot reject H naught. Our claim was H alpha, so therefore, at the 1% level of significance, there is not enough evidence to support our claim that the proportion of the population who prefers dark chocolate is greater than 60%. If you desire, instead of comparing the z-score of the test statistic to the rejection area defined by the level of significance, you could employ method 2 and use a p-value to perform the hypothesis test. Under this method, we must again verify that n times p and n times q are greater than or equal to 5. Then we write our H naught and H alpha. Next, we get the value of the test statistic and find its p-value. Remember, a p-value is derived from the area in the tail of the test statistic. In a one-tailed test, the area in the test statistic equals the p-value. But in a two-tailed test, the p-value equals the area in the tail of the test statistic times 2. Finally, compare the p-value to alpha. If the p-value is less than or equal to alpha, there is enough evidence to reject H naught. If the p-value is greater than alpha, there is not enough evidence to reject H naught. For this problem about the chocolate lovers, we would have calculated the value of our test statistic, 1.02, and from the z-table, gotten the area in the tail of that test statistic, 0.1539. As it is a one-tailed test, this equals our p-value, which we now compared with alpha. Since the p-value is greater than alpha, we fail to reject H naught, and therefore there is not enough evidence to support our claim. Next, let's consider hypothesis testing for variance and standard deviation. Just as in our previous hypothesis testing examples, we must verify the population is normally distributed. Then we make a claim, assign it to either H null or H alpha, and write its complement. Then we identify alpha and find the critical value or critical values based on the level of significance and on the degrees of freedom, which comes from the sample size. More on that in a moment. Next, we calculate the test statistic and compare it to the rejection area or areas, and then we interpret our decision to reject or not reject in the context of the original claim. To get a critical value or critical values for variance or standard deviation tests, we use the chi-square table. Remember, if you covered this in Chapter 6, a chi-square distribution is really a family of curves, and the table gives scores based on areas to the right and on the number of degrees of freedom. For this type of problem, we use n-1 degrees of freedom. For example, if my alpha was 0.05 and I am conducting a right-tailed test with a sample size of 19, I go down to the row for 18 degrees of freedom and find the column for alpha equals 0.05 to get the critical score of 28.869. Another example, if my alpha was 0.10 and I am conducting a left-tailed test with a sample size of 10, I go to the row for 9 degrees of freedom and find the alpha column for 0.90 as the level of significance, 0.10, is in the left tail for this left-tailed test. But as the table gives areas to the right, and as the whole area under the curve is 1, then the area to the right of this position is 1 minus 0.10, which is 0.90. And so I get my critical value of 4.168. One more example. How about a two-tailed test with an alpha equal to 0.01 and n equals 41? That gives 40 degrees of freedom. In a two-tailed test, the alpha is split in half. So half of 0.01 is 0.005. The left critical value, called chi L squared, has an area of 1 minus 0.005 to the right, which is 0.995. Find 0.995 with 40 degrees of freedom, and you get a critical value of 20.707. Find the chi R squared number for an area to the right of 0.005 and 40 degrees of freedom, which gets us the critical value of 66.766. Once you have your critical value, calculate your test statistic and see if that value falls in the rejection area or not. The formula for the test statistic for a variance test is the same as for a standard deviation test, and that formula says chi squared equals n minus 1 times s squared over sigma squared. For sigma, assume it has the value given in h0. Once you reject or fail to reject the null hypothesis, you can interpret what that means for your claim. Here's an example. A manufacturer claims the standard deviation of the diameter of their bolts is less than 0.17 millimeters. A random sample of 20 bolts has a standard deviation of 0.13 millimeters. At alpha equals 0.10, is there enough evidence to support the company's claim? Assume the population is normally distributed. First, write out the claim. Sigma is less than 0.17 millimeters. That condition does not contain a condition of equality, so it is our H alpha. The H0 is the complement, which is sigma is greater than or equal to 0.17. This is a left-tailed test, we know, because of the direction of the inequality in H alpha. And going to the chi squared table, we'll find the row for 19 degrees of freedom. And for the column, using 1 minus 0.10, which is 0.90, we identify a critical value of 11.651. We can shade in the rejection area, which is an area to the left of that position. Now we perform the calculation for the test statistic, which says chi squared equals, so that's 20 minus 1, times 0.13 squared over 0.17 squared. That equals 11.111. The test statistic does fall in the rejection area. Therefore, we have enough evidence to reject H0, but our claim was H alpha. So we would say that at the 10% level of confidence, there is enough evidence to support the claim that the standard deviation of the diameter of the bolts is less than 0.17 millimeters. We have now looked at examples of hypothesis testing for mean, proportion, and for variance and standard deviation. Some students may be asked in Chapter 9 to do hypothesis testing for correlation, or in Chapter 8 for testing the difference between means. Look for these topics in a future video. Let us know if there was anything in this video that could be made more clear for a future update, and let us know if there are other videos you would like to see in this series. As always, check out our website for more information about services available in our Learning Success Center, or call email, or stop by. Good luck, and I hope to see you this semester in the Learning Success Center.